Hello, everybody. I guess, can we already see the slides? Oh, here they are.
Yep.
I guess most of you do know Lufthansa as an airline company. You know, the company which brings you from the United States to Europe or any other place over the world. Lufthansa Industry Solutions is a consulting company for IT and analytics issues, and we are owned by Lufthansa. We are around about 1,500 consultants in Germany, here in the US, but also in other countries. And we consult companies over different industries. So we are not focused on aviation. We, of course, consult companies from the aviation business, but also from the manufacturing, from industry, from energy sector, from health sector. Here in the US, we do have our office in Miami, and consult from their US-based or North America-based firms on how to use data in their business. My name is Stan, and I would like to show you today an audio recognition case, or how do we use audio data to recognize maintenance issues. I usually start this talk with an introduction of what is IoT, what is analytics. But you are all data scientists, as I recognize on the questions and on the participations you do and the discussions we had. So you do not need this introduction. So let me tell you a little bit another story as introduction for the use case. As I said, I live in Miami, and some time ago, my wife and our daughter, we were on one of these huge cruise ships leaving Miami like every day. And since Wi-Fi is quite expensive on such a ship and very, very slow, adults start to do really weird things. We went to an art auction. I've never been to an art auction. I will probably never go again to an art auction. But here on the ship, I was on an art auction with my wife. And on this art auction, there was a gentleman, and so the auctioneer. And he was like, sorry? Louder? Yes, sure. Can we? So this gentleman on this art auction was introducing the pictures. And he did a really great job. But he did it in a very sales-intensive way. You know, he was saying things like, this is a unique canvas. I have no idea what picture is a canvas, but this is a unique canvas. Or those are breathtaking colors. Or this is the most outstanding painter. And after some time sitting there and listening to this gentleman, I wanted to buy a picture too. And here's the thing. I have no idea about art, and I do not know whether what the gentleman was telling me was right or not. The reason why I'm telling you this story is in this situation, or this situation reminded me very much on the one or the other analytic sales speech I have seen in my life with my customers or with our customers in the business world. So they were kind of, how to say, like show masters presenting great slides. And even though I was thinking, I'm not sure if this is possible with a data science background, I wanted to buy it. Do you know the situation? We at Lufthansa Industry Solutions decided to go a slightly different way. We built prototypes. For many of our projects, analytics projects we've done so far, we built prototypes. Those prototypes do not need to have access to a data warehouse. They do not claim to have the best model in the system right now. But those prototypes show how the results will look like. They give the customer the opportunity to try it in the business and to see what will be the impact in the business, and will there be an impact at all? Is that what I want to have? And it shows very well what we can do, and it also shows what we can't do, which is more important in data analytics right now, as I see. And such a prototype, I would like to show you today. You see part of this already here. built by German engineers in Germany and data scientists from our team. And before I show you the prototype, let me go through the use case so you have a better understanding why we have built this one. Here is the use case. This is actually a real use case from the real business world. We do have a customer who operates more than 1,000 escalators. Escalators, those rolling stairs. 1,000 is quite a number, more than 1,000. So each time the escalator is not working, it has a downtime, the customer has either to pay a fine and does not get any money for the escalator. Very easy. And if the escalator has a downtime, then the customer usually gets this information from an external source. So somebody calls him and says, hey, look, the escalator is not working. Of course, the customer wants to reduce the downtimes and to earn more money. This is the whole idea behind this use case. So the customer approached us and asked, can you build any kind of model? We have heard so many things about data science, data analytics, AI in the world. I mean, it must be possible to build an analytics model, kind of predictive maintenance, to see whether the escalator is working or not working, or maybe a little bit different, whether the escalator does need maintenance or does not need maintenance. Okay? And then the customer has a maintenance team which goes out and does the maintenance. Okay, for many of you, an easy task, right? Classification problem, go ahead, easy. We had some preconditions. No changes on the machines. So we're not allowed to do any changes on the escalators. Any add-ons we would like to add to the escalator should be at low cost. No Wi-Fi at the escalators, and no data science team implemented right now and will not be implemented. So we were looking for a one-click solution. This was the information where we started working. We started with a hardware side. On a hardware side, we had the opportunity to go with a fill sensor, like for the liquids, a vibration sensor, and an audio sensor. So the fill sensor is quite expensive to install. The vibration sensor needs some changes on the machine. So the winner was very fast, the audio sensor. Audio sensor, microphones on Amazon, 99 cents. Easy to install and not so costly. Since no Wi-Fi was available, we needed to work with a local computer. And low-cost requirement limited us in a high-performance edge computing. So it was the very fast decision to go with a Raspberry Pi. And the last kind of challenge was to find an analytic solution, so a model which will work unsupervised, because we did not have any labeled data, and collecting labeled data would require some cost. So we needed an unsupervised model which should be very efficient, CPU efficient, because we are using a Raspberry Pi. So we could not go with, maybe with cluster we could have gone, but not with, we could not work with GANs, or any other models would require more computer power. So we came up with the isolation forest, which is a very efficient model for outlier detection. And this in total was then the background for the prototype. How many of you have already worked with an isolation forest? Have heard about isolation forest? Okay. Isolation forest is basically an outlier detection method. It's a model-based approach which directly identifies outliers instead of profiling normal data points. And because it does directly identifies the anomaly points, it does need so many computer power. In a training mode, the isolation forest starts on a random point, builds a number of trees, which divides the sample, and calculates the number of steps it needed to isolate those points, and this on average. In the prediction mode, as new data come in, it also isolates the data and calculates the number of steps it needed, and then compares it to the training set. The whole idea behind this, if the data, if we needed a lot of steps to isolate the data, then there's a lot of data close by. Then it will be not an outlier, not an anomaly. This is what you see here on the left side of this feature. But if the data point is outside of the crowd, then it's highly likely that this is an outlier. In our case, this is a maintenance issue. And then the number of steps is low. And this is the magic behind this. You will find the reference on the slides. Feel free to download the paper. Authors, they describe it very well in detail. For those of you who haven't worked with audio data, an audio signal is recorded by sampling 44,100 times a second. This is quite a lot of data. And of course, in this data is also quite a lot of noise, so we do not need a lot of all these data points. So what we did, we compressed this data to 192 times per second and calculated a number of features which all in some way describe the sound. It's a tone net, it's a power spectrum. Those features describe the sound. We have worked with more and less features, but after a couple of tests, we found that this one, would, the 192 times per second, was efficient enough to build a good model. That's it about the theory. Let's see how we set up the prototype. You can see the prototype here, and it will also be here like in for the next couple of hours. Feel free to come around and see this in more detail. So what we do have here is basically a ventilator or a fan with a regular on-off button. And if I put it on, it makes some noise. We do have here on this side a power supply and a Raspberry Pi. So on the Raspberry Pi, we have installed the model where we train and then work with prediction model. And we have built a web interface, which I will show you now. We have built a web interface where you see two buttons. It's not a one-click solution, it's a two-click solution. But the two buttons, you train and you predict. So the prediction mode is actually the operational mode. And now let's see how it works. So I guess you all can see it is working. So it's really working. It does make some noise. Let me go maybe this one. Yeah, so you can now hear it. So what we would do as the first step is to train a model. A model is trained on the normal data. We do not need the maintenance data. We are training this model on the normal data. In a laboratory environment, 45 seconds are enough to get a model with an accuracy rate of over 80% in a laboratory environment. So it's calm and no other noise. In an environment with more noise, we need 2 to 3 minutes. So our suggestion in this case would be go for 5 minutes. As soon as the 5 minutes are over, we would have a good model to run and implement, or it's already in the system. So let us not wait the 5 minutes. I've already trained a model just a couple of minutes before the presentation. If I now start the prediction mode, you see the green bars. So the green bars are indicating, still the model 1, yeah. The green bars are indicating everything is fine. You see I've trained the model in the coffee break, and in the coffee break they were kind of noisy, people were speaking. So it now thinks if I speak, everything is all right. Now, we could wait for a maintenance issue, but as I said, this is German technology. This will never break. So let's simulate a maintenance issue. A maintenance issue could be, so if you think of an escalator, there are two main maintenance issues. One, which happens quite a lot, is if a penny gets into the grid, right? Then it makes this special noise. This is not a maintenance issue right now, but it will become a maintenance issue if you do not pull out this penny out of the grid, because it will go into the motor. And so this is one possible source. So I will simulate this. I will have a cable binder, and I will put it into the ventilator. You see, this sound is definitely not okay anymore, and the model recognizes, oh, no, let's see, I do have a maintenance issue. Of course, a maintenance issue could also be very different. It can also be like knocking at the motor. You know, the motor can be break. Let's simulate this. We could do any other simulate any other maintenance issue. So the model would recognize them. Of course, not every red bar is a maintenance issue. So there are then some criteria where and after what time period this is a maintenance issue. It wasn't me. Maintenance? I don't know. Oh, it was me, sorry. Of course, there are some criteria. After some time, if we have the maintenance issue, then it will send out, we have installed a SIM card, it will send out the information to the maintenance team saying, hey, look, I am escalator 848. Please come around and look at me. Something is wrong with me. Right? So, let me show you my last slide, which is basically then the application of this. Depending on the length of the escalator, we install microphones on it, 1 to 4, to have a Raspberry Pi on it. Then the Raspberry Pi analyzes the data and sends out this information to the maintenance team. So sometimes people ask me, so what is the benefit of it? Do you reduce the maintenance issues? No, we don't. We do not reduce the maintenance issue. We reduce the downtimes. Because now a company, the customer, does have the ability to know in advance something will go wrong. So he goes out, and if the maintenance team is there, then this is not a downtime. So the company is still getting paid, or does not get a fine for this one. So we are reducing these downtimes. And using a very simple application, Raspberry Pi and a ventilator and an isolation force, these are like all not really magic. This easy application helped the customer to reduce the downtimes and to earn more money. That's it, how we use analytics, audio analytics for this case. That's from my side. Thank you very much. We do have a question here.
So the question is regarding manufacturing product. Okay, so now you're building this product in a factory, you have outgoing quality inspection. Do you know any companies that are using the sound signature and machine learning in order to verify that the equipment is operating correctly as it leaves the factory, just brand new, having been manufactured? And the second part is, during the design phase, it's common to do a failure mode effects analysis, or FMEA. Have you done any training of the sound signature for different types of failings, like worn bearings, unbalanced turbines, and things like that, so that not only can you tell that something is wrong, but you know what is wrong because you've mapped that signature?
Mm-hmm. Let me ask the second question first. In this project, we didn't, because we did not have the available data, and we would have the opportunity to go out. But it was a project for a couple of days. So we did it very fast and delivered the solution for the customer, and the customer said, yes, we do it. But after we have built this prototype, of course, we are showing off with this prototype for a consulting company. We earn money by selling this kind of stuff. Customers ask us to do exactly this. But this is then a little bit different problem, because if you try to say, okay, this is wrong or that is wrong, then it's not anymore unsupervised. So we would not use the isolation forest for this one. We would use a clustering or maybe a account model for identifying this specific problem and telling, right, so we would tell the maintenance team, okay, if you go out to this machine, we expect this is wrong. So for this case, we would use another algorithm. This algorithm simply says something is wrong. We do not know what, but something is wrong. So the maintenance team goes out, has all its equipment with it, and then looks, oh, okay. Mm-hmm. And the first question, can you repeat the first question?
Outgoing inspection and manufacturing.
Yeah, in Miami, the cruise ship companies are all our customers, and this is a big use case for them. Right.
Thank you. I have a question. In your model, how do you distinguish between the noises produced by the system versus the noise produced by the environment? I imagine the escalator can be applied in different situations, like supermarket, airport, all kind of places, and the passenger may create some noises. How does your model train for those kind of scenarios, and how do you prepare for that?
The model doesn't. The criteria after this does. So if you're on an escalator, so depending on the length of the escalator, it takes you like 20 to 40, 50 seconds to go down. So the criteria let's imagine somebody is on an escalator and, I don't know, looks a YouTube video on his iPhone very loudly, right? So in this case, the solution would identify this sound as not normal. So, but this would only take 20 seconds. After 20 seconds, the person would be gone, and then the model would return to green bars. So the maintenance issue notification is sent out using this duration criteria. After 20 seconds, if the maintenance issue is ongoing, if the red bars are ongoing longer than 20 seconds or even longer, then we say this is a maintenance issue. Everything what is shorter is not supposed to be a maintenance issue, because cases there are kids on an escalator which are jumping around or something like this, and all of this would generate a lot of false maintenance issues notifications, which we of course also do not want, because then you do not earn money, you have higher costs, like sending out the maintenance team to the escalator. Mm-hmm.
So this is really impressive. I can see a lot of application in the traditional industries. I wonder, in addition to the audio analytics, are there other type of analysis on the IoT devices? For example, I recently read an article talking about the motion sensor on the windmill blade. So for windmills, the blade, because different areas have different patterns, so you don't know when to replace one. So they place the motion sensors on the windmill, and then it helps them to track the utilization and determine when to replace one, and also to determine which area is good for to utilize wind resources. So I just want to know if you have analyzed other type of IoT devices.
Temperature and vibration would also be, that's why we used, as we were thinking about what kind of sensor we will use in this case, we also were thinking about field sensor and vibration sensor, because we do have use cases where we have already worked with those kind of sensors. But here, so this case, as I said, field sensor is expensive to install because you have to go to inside the machine and put it in, and it costs a lot of money. However, there are 1,000 use cases, and I heard a very interesting phrase in English a couple of days ago saying you can boil the ocean with it. Yeah. So I guess the number of applications is huge. The reason to think about is it worth to do this from the business perspective? And business is actually paying us. And for a number of customers here in Miami, we are working on use cases which use also another sensor. But in this case, you have to go with a little bit more high performance computing, because I mean, the Raspberry Pi has definitely, it's a great, it's low cost, but it has its limits where you cannot analyze a lot of data or cannot maybe not run the one or the other algorithm. Here we had the question. Excuse me.
So if your objective is to minimize the downtime, how did you test that? Did you actually see that the downtime is less? Because if it only takes like 20 seconds to train, you can't model every single situation within that time frame. So I'm imagining that every time it encounters a new situation, a new noise, it would just interpret it as a maintenance issue. So that would actually contribute to more downtime, not decrease it. And so how do you make that balance?
First of all, we do train the model on normal data, so not on the maintenance data. So, and then the model recognizes everything what is not normal as maintenance. And then using the criteria, we are able to say, okay, this is not a child on an escalator.
How do you avoid false negatives? Because you can't account for every single situation.
In a laboratory environment, we can track this, and we can analyze whether it was a false negative or not false negative. In a real environment, we are aligned to what the customer is saying to us. And the overall results of the customer's downtime were after implementing the system, the downtime went down. So how many false negatives they had in this case, we do not track. But in a situation with, in a laboratory environment, we had an accuracy rate which met and identified the points right, was 81%. Again, in a laboratory environment. We had a question also over here. From the guy here says with 1 minute left.
I was going to ask you about the remaining lifetime estimation. Have you ever considered applying this model, or like other projects that you utilize the remaining lifetime estimation for these devices as the data shifts through outliers?
The remaining lifetime estimation from the escalators or from the Raspberry Pi?
Or escalators, or in any other projects?
Not in this case. Again, it would require the more information, more historical information, which we did not have as we started this project. But of course, after running this to need. But we also do not keep the data because space is limited. And so anytime there's a regular maintenance schedule for those escalators, and it will be retrained. So we actually do not keep the data, which would require the lifetime estimation from the escalators. There's one last question, if you have the time, otherwise with a coffee or something like this. You are the time.
All right. I think we got it. All right, Stan. Well, thank you very much. Appreciate it. Another round of applause for Stan.
Great. Thank you.